let me start with a real part of the talk. So I will be interested in Lp-cohomology, and let me first introduce what that means. So I'm looking always at a gamma, a finitely generated group. And you should think of this group being infinite in general. So now what is Lp-cohomology? So what we do is we look at cocycles. So it's a cohomology theory. We look at cocycles modulo coboundaries. And what is a cocycle? A cocycle is a function C from gamma to Lp of gamma. So here we have a countable group. Our group is finally generated. So Lp of gamma is just the space of Lp integrable functions on the group, where of course the functions is a function on a countable set. And we want that the Lp integral is finite. Now, what we do is a cocycle. So I wrote it already down. Is has the following property: C of G times H. So we can have group multiplication, and this is supposed to be equal to C of G multiplied with G of C of H. And the action of G, I write it down from the left, but GF is equal to F composed with G minus 1. So you let first G act as G minus 1 from the right, actually. So, and then you apply F here. So you first let act G and then you apply F. So that's a standard way to write down the left action of a group on the space of functions. Now, what is a coboundary? A coboundary is such a cocycle which can be written as GF. So again, I write now the action of G on functions from the left, GF minus F. So if you plug this in, this is a special type of, plus, sorry. This is a special cocycle here. And now what we do is we take H1 of gamma in this coefficient, and P of gamma is equal to cocycles mod coboundaries. And now we can, we realize we are in infinite dimensional space. Maybe it also makes sense to take the reduced cohomology, which is the one I'm really interested in. So that's reduced. And now you close up the space of coboundaries. So very clearly you get a smaller space here, but it's still a nice space. Well, that has better properties, which will not be relevant for this talk. Now the question is, what can we say about this? And there's of course a lot of work in this direction, including work of Bruce. But my talk here, what I'm going to talk about today, will be inspired of metric analysis, actually. And this is inspired by some other work of Bruce that he did together with Mario Bonk. So now what we can say about it. First, I want to not restrict to this function space here. So we can take now any, say, V, any Banach space. And I want this Banach space to be an LP space. For the sake of this talk, meaning it's a space of LP integrable functions on some space with measure. And then we can look at rho, a map from gamma into the isometry group of V. The isometry group, so that's supposed to be a linear representation. And then we want this cocycle to have values in V, and the definition of a cocycle is exactly the same thing as you see here. And what does a cocycle mean? So if you have a full isometry, the full isometry group of V is a semi-direct product of the linear isometries, let me call this way, and the space of translations. And now a cocycle means you have actually an action on the group where the linear part comes from the given representation here, but now you have a translational part, and the translational part is given exactly by this cocycle. And what you want is that this cocycle somehow goes away from the origin. So this is the relation here. This is this cohomology theory tells you somehow the non-triviality of the linear part of this action. So there are many results that study this situation here. There's one result which I find is striking. So, which is a theorem which was mentioned already in Cornelia's talk. So the theorem is due to Bader, Perelman, Gerlander, and Monod. And what does the theorem say? If gamma is a lattice, any lattice, for simplicity, I do not state the theorem in full generality, but in a simple Lie group, non-compact type, and rank, real rank of G is bigger or equal than 2, then this first cohomology, I mean, even the first cohomology, not just the reduced one, as I try to explain to you, the reduced cohomology is always smaller than the real cohomology. So I mean, the non-reduced cohomology. So then gamma, H1 of gamma, this coefficient in V is equal to 0 for any Lp space V, regardless what the representation is. So we can take any representation of gamma into the isometric group of some Banach space, which is an Lp space, and then this cohomology vanishes. And this was strengthened by Delade and de la Salle. This is actually very recent. This preprint came out this year, and they showed that this even true if V is any what's called uniformly convex Banach space. So what this means is that lattices in simple Lie groups of non-compact type and higher rank have no non-trivial, in some sense, non-trivial actions in this sense here on Lp spaces or uniformly convex Banach spaces. So on the other hand, there is a theorem which was also already mentioned by Cornelia. There's a theorem which is due to Guliang Yu, and it says if gamma is a hyperbolic group, hyperbolic in the sense of Gromov, and this, since this was introduced a couple of times already, I will not introduce this anymore, then gamma admits a proper action on an Lp space for some P. And what means proper? It means it's an isometric action. So you have a representation. This has a linear part. Then you have this cocycle, which gives you the translation. And this cocycle moves away from any bounded set as you go to infinity in the group. I will not write this down here, but in particular, it means that the reduced cohomology of gamma with a coefficient in this V is not equal to 0. So that is a striking difference. And of course, as Cornelia already pointed out, these groups may have strong rigidity properties. They may satisfy Kashtan's property T. Now, what I will be interested in is, I will be interested in trying to construct representations of groups which have some nice properties, meaning that they're different from these guys here. And they're only also different from hyperbolic groups, because for hyperbolic groups, pretty much everything is known from that point of view, which gives us non-trivial reduced cohomology with representations or with coefficients in an Lp space. And we will use the metric analysis to this end. To this end, let me introduce a few more notions which also should be familiar, namely what it means for an action on, say, a hyperbolic space. Now, a group can act isometrically on hyperbolic space, and I like to tell what it means to be an uninteresting action. So the following definition, which is probably familiar to many of you, an isometric action of a group gamma. Again, my group is always finitely generated in a discrete group. So on a hyperbolic space, hyperbolic in the sense of Gromov is elementary, or say I now write non-elementary. So because I want to single out the interesting property or interesting actions, if there are at least two independent loxodromic elements. And I will tell you what that is. So what does this mean? It means that the group acts on, and the loxodromic element will be the one which preserves a quasi-geodesic. So at the moment, I'm not assuming anything about my hyperbolic space here. It doesn't have to be a proper, meaning locally compact. But what I want at the end of the day is that there's a sort of geodesic, or say roughly geodesic or something or other. So meaning that you can talk about what a geodesic is, or a quasi-geodesic or something like this, and to be preserved under an element of the group. And what I want is that at least two elements which have such an invariant quasi-geodesic acts on these by translation, and such that you have an attracting fixed point, the translation length is positive. You have an attracting fixed point on the boundary of the space and a repelling fixed point. And then I have another one, which has also an attracting and repelling point, which is fixed on the boundary of the Gromov hyperbolic space. And I want that these fixed point sets are disjoint. So these are the interesting actions that do not factor through an action of an abelian group, say, or that do not have a bounded orbit. All right. So now let me come to the specific example, so which is familiar probably to most of you, which is a Hadamard manifold. Is simply connected, complete manifold of, now the standard definition would be of non-positive curvature, but I really want of negative curvature. Let me just state the correct definition of non-positive curvature. So the sectional curvature is less or equal than 0, but I want now bounded geometry, which means that the sectional curvature is contained in an interval of the form minus b square minus a square, where a is a positive number and is less than b or less or equal than b, and b is of course not infinite. So now let me state a theorem that will be a consequence of what the real theorem is, but which is maybe easier to appreciate. I actually don't know whether the theorem is really new, but let me just state it. The theorem is as follows. Assume gamma admits a non-elementary isometric action on a Hadamard manifold of bounded geometry. So notice that I'm not requiring that the action is proper, meaning the action might have non-discrete orbits. So I'm not assuming anything. I'm assuming that my group gamma is finally generated and that I have this Hadamard manifold of bounded geometry. Then there exists a P and an LP space B such that the cohomology, the first cohomology of gamma with coefficient in V and the reduced cohomology is not equal to 0. So there are lots of works in this direction. Let me just mention here Pensu, Baudon, Sorry, thank you. P bigger than 1. Thank you. It's early in the morning. Thank you. So P is bigger than 1. And of course, and sometimes you want to control the P, but I don't know how to control this. So there is some P and an LP space V such that this reduced cohomology is not equal to 0. So there's earlier work, Pensée, Bourdon, Pajot, say, Bourdon, Kleiner. And maybe these people actually knew these results, except that I could not trace this in the literature. Because what I didn't find in the literature is what you do if the action is, say, non-discrete. So let me now try to explain to you what the relation is to metric analysis. This relation has been studied by Kleiner and Bonk, and also by many other people. So there is work by Bonk, Heinonen, and others. And what they do is they try to understand what the structure of the boundary of the hyperbolic space is going to be, and uses to understand properties of the group action. And this is exactly what I'm trying to do here. So let me make the relevant definition. So we start off with something that is really metric analysis on the boundary of this space. So the boundary of this Hadamard manifold, let me write this down just for the sake of completeness, is a space of geodesics, of geodesic rays from a point P in M triple. So it doesn't matter which P you take. That was actually the same P, so let me take X in M triple. So that is a nice space. So in this particular case, it's a compact space, but it has a metric, and what's called a visual metric. How does this go? So we define the visual metric as follows. So you take your point X, then you take two rays coming out of X. So now you take, say, this is gamma 1, and here's gamma 2, and these defines point at infinity and the boundary. And now you define the Gromov product. So let me call these points psi and eta. Between psi and eta at the point P, this is equal to the limit as t goes to infinity. Now you take 1/2 for aesthetical reasons, and then you take the distance between X and gamma 1 of t, which is t, the distance between X and gamma 2 of t, which is t, and you subtract the distance between gamma 1 of t and gamma 2 of t. So that's a Gromov product. So in other words, you go out, you look at a triangle here, and you ask yourself, okay, how do you describe the triangle? This triangle here has two sides. One side has length t, the other side also has length t. That is just an artifact of the way I write it down. And then you look at what the side of the third side is, and you have the thin triangle property, which means that the third side is always in a neighborhood of the other two sides. So how the neighborhood looks like, depending on how close these rays are together, well, this is captured by this Gromov product. And now what Gromov showed is, so there exists a number, now comes a different, an epsilon bigger than 0, such that you have a visual metric and a metric, the visual metric on the boundary, which has the following property. So this metric d of psi eta is contained in, say, fixed constant times e to the power minus epsilon, the Gromov product of psi and eta, and e to the power minus epsilon of psi and eta. So that is, in other words, you can control it, and A is a fixed positive constant. So that's this visual metric. And if you have a metric space, well, now we have a metric space. This metric space depends on X. We will come back to this a little later on. But now we have this nice metric space, so we can look for metric analysis on the space. So now what we want is that this metric space has nice properties, and there's a doubling property. So what is the doubling property of a metric space XD? So it means that there exists a number C bigger than 0 such that for all R bigger than 0, the ball and all X in X, the ball of radius R about X can be covered by there exists C bigger than 0 by C times C balls of radius R over 2. There, so you take balls of radius half the radius whose radius is half of the given radius, and then you ask yourself how many balls of the smaller radius do I need to cover my original ball, and you do this for every R. And this is if this R here is finite. So if the C is finite for all R and all X, then the space is doubling. So there are many different ways to express metric spaces which have nice sort of dimension properties, Urs Lang has already alluded to in his talk. But this is sort of a hands-on definition which will be good enough for our purpose. Now, what do we know about this is, so there is a theorem by Monk and Schramm, and I actually also don't know whether this part of their theorem was known earlier, but I'm not so sure about this, which says that if this Hadamard manifold has sectional curvature in minus b square minus a square, again, a and b are positive numbers, then the boundary is doubling. The boundary with respect to the visual metric. And so if you take one visual metric for one point, then it's also true for a visual metric of any other point. So you just pick a point, and then you ask yourself, is this a boundary doubling? And Bonk and Schramm showed yes, it is true, provided that you have here this curvature contour. So you cannot expect too much. If the curvature goes to infinity, you are definitely in trouble. Now, this is not the main part of their theorem. What they proved is actually there's something more interesting going on. Furthermore, up to rescaling M twiddle. So rescaling meaning with a fixed constant. You rescale the metric. M can be roughly isometrically embedded into HM, hyperbolic space, constant curvature for some M. So the M is not the dimension, this is not the dimension of your regional manifold. So now that is a beautiful theorem, and we will not be using it. What we will be using is the spirit of the theorem. So how did they do this? They used the fact, which is due to Assouad, which says the following: if XD is doubling, so now you have a metric space which is doubling. So my metric space you should think of as a boundary of a hyperbolic space. If this is doubling, then a snowflake. What is a snowflake? We have seen this before. You replace D by a power, which is still a metric. But of course, I mean, as Urs Lang pointed out already, this destroys all paths of finite length. But you can take the snowflake, and then a snowflake can be, some snowflake can be isometrically embedded into our M for some M. Sorry? by Lipschitz, sorry, not by Lipschitz, thank you. I was ahead of myself. And thank you. So the whole point of this is, so by Lipschitz, what does it give you? It gives you a nice measure. So what it gives to you is, and this will be of importance, so the consequence is, so sorry, I should have said, thank you, Mario, for your comment. I should have said, so what do they do is they use Assouad theorem to get the boundary embedded, and then they have a construction which embed the entire space into hyperbolic space. That's a beautiful construction, which I will not use. So what I will use is the consequence is of this, of the theorem of Assouad, is that there exists an alpha homogeneous. So I will not be interested in computing dimensions here. So there is some alpha, and there's an alpha homogeneous measure mu on your original space. So this space for the moment is a boundary of my Hadamard manifold. So what is the alpha homogeneous space measure? Sorry. It's a measure which has the following property. So the alpha here has to be bigger than what's called the Assouad dimension. I will not talk about the Assouad dimension. For us, all what matters is there is this alpha, or some alpha. And what does it mean to be alpha homogeneous? It means that mu of bxr over mu of bx big R. So you take a point in your space, you look at the radius, which you think is smaller than the radius below, and this is supposed to be bigger or equal than some constant b times r over r to the power alpha. And now we have this measure. So we think about this measure sitting on the space here. My space was doubling. We have this nice measure here. And now what we try to do is we try to relate this measure to the action of the group. But what does this measure has to do with the action of the group? Nothing, of course. So now the question is how can we consolidate this situation here? So to get an idea how to do this, let me give you an example. This was actually the motivating example for me to come up with this work. This motivating example is very simple. So you look at gamma, a Kleiner group. So a Kleiner group is a discrete subgroup. All my groups will be finally generated, but it's a discrete subgroup of PSL2C, which is the isometric group of hyperbolic three space. Now, what is the boundary of hyperbolic three space? So the boundary of hyperbolic three space is equal to S2, the round two sphere. So how does this group act on S2? So S2 is nice. So this S2, we think of it as being embedded in R3 as the round two sphere. So how does this relation go? You pick a point in the hyperbolic three space, then you look at the boundary at infinity, so the Gromov boundary seen from that point. This boundary is S2 with a round metric. So visual metric is just a round metric. And now what we know is, so a round disk in S2 is the intersection S2 intersected with a half space in R3. So, I mean, what you just do is, okay, I mean, you take your round S2, right? And then you just intersect it with a half space, meaning you just take an affine plane and intersect the sphere with this affine plane. And then this divides the sphere, typically, if it does intersect, into two components. One is a disk on the top, and the other is a disk on the bottom. So one of these components is around a disk. And now what this group does is, so gamma maps round disks to round disks. So that's a remarkable property. If you know about metric analysis and quasi-symmetric maps, this group is not uniformly quasi-symmetric. My group is infinite. So it's not supposed to be, say if it's supposed to be discrete, now for the moment it's infinite, it cannot be uniformly quasi-symmetric, but it does map around this. So what does it mean? So let's just take an loxodromic element in the group. So it has two fixed points on the boundary. My boundary is S2. And now how does it act? There's what's called an isometric circle. An isometric circle is the boundary of a round disk. This is mapped isometrically to another circle, but the other circle may be very far away. So this circle is very close to the repelling fixed point, which is eta, and it maps this thing isometrically. So the length of this circle as a circle in the round two sphere is the same as the length of this circle here. So it maps this thing up to here, but then it maps everything what's on top. There's no colored, oh yeah, there's colored choke, sorry. Maps what is on the top of this circle, this part here, maps it into here. So meaning it contracts everything which is on the top of the circle to the smaller region, and it expands everything which was on the bottom to the region, to the bigger region, right? So what does it mean? I take now point here on the boundary of this isometric circle, and I look at the round disk. Where does the center go? The center goes to a point on the isometric circle, but the circle, the image of the circle doesn't look the way from the point of view of the isometric circle at all anymore in the way this circle looked, because this region is contracted. So this region becomes very small. This region is expanded, becomes very big. That is maybe not the right scale here, but what I'm trying to say is the center of the circle moves very close to the boundary. So this maps the circle, this circle here, which is the boundary of a round ball. It maps it to this circle, but the center goes very close to the boundary of the image circle. So this makes this map as if the translation length becomes very large, very much sort of non-quasi-symmetric. It's still quasi-symmetric, but the constants go through the roof. All right, so, but we are ultimately interested in looking at measures of round balls, and we are not interested in where centers goes. So we want to use the measures to construct actions on LP spaces. So that is sort of more promising if you just look at balls and try to study their measure. So to this end, let me make a definition which captures in a slightly more abstract way this property that this Kleiner group has. So for C bigger than 0, a homeomorphism phi of a metric space, and now I want the metric space to be bounded. Boundaries of Gromov hyperbolic spaces are always bounded, or bounded metric space. X is C quasi conformal if for all x in X and R less than the diameter of X over 2. So bounded means a finite diameter. Now I have the dilatation of my map at the point X. So I have dilatation phi of, and now at the point X with radius R, XR, this is supposed to be the supremum of all d phi X, phi Y with Y in the ball of radius R about X. There exists a Z in X. And this is the Z plays a role of the center of my image disk, which is not the image of the center in general, such that BZ, and now C times dilatation of phi XR, is contained in phi of XR. Now, if you think about the example that I just gave you with the Kleiner group, so for the Kleiner group, I mean, I did the definition in such a way that you don't get C here to be equal to 1, but for the Kleiner group, we easily see, for the reason that I just told you, that round disks are mapped to round disks is Kleiner group. C can be taken to be 1/2. So, and I just want that there is a uniform C. So that will be capturing the fact that my map maps this or round balls to round balls more or less, but the center might go anywhere. So there's no control in the center. Now, this is good news, because since we are ultimately interested in controlling masses here of balls, so this gives us a leverage of controlling masses. But there is a problem here, and the problem is the following. So we don't know that our metric space has any nice properties to begin with. So it might be sparse in some places, meaning that you look at a point and you look at a ball around it, there may not be so many points around it. So like if you think about a Cantor set, right, a Cantor set that has holes, so that may be bad news for basically controlling measures. So we will need some other properties of the metric space to make sure that we have enough points that at the end of the day, we can have a comparison of masses of balls, and then use this fact that we have now control masses on balls to construct representations of our group onto some LP space. So what will be the definition? So I have now to make another definition, but it's kind of elementary. So I call a metric space XD is called full, which has, so full means it has many points. If there exist constants 0 less than E, less than B, less than 1, say, with the following property. So we take X not equal to Y in X. And so suppose that the distance between X and Y is equal to some number R, which is positive. And then for all, and here now for all rho, which are now controlled by the radius, so rho less than equal to B times R, so B is smaller than 1. So we scale down a little bit. There exists a point Z in B X rho minus B X B rho. So now we take here some part from the ball, meaning we take now a shell around the point X, but a shell which is given by these two constants, rho and B rho. So rho is smaller than my original ball, so I want to scale in. But then I look at the shell, and I want that this has some non-trivial points. So there are points in it, which would amount to the uniform property condition, but I want actually more. So there exists a point Z such that the ball of radius E rho about the point Z is contained in the original ball. So meaning that there is a point Z in something on the right side of some half space or some half ball defined by by the given constants here. So in other words, so here's my big ball, right? Then I have a smaller, so then have a smaller ball. Here's my point X, right? And now what could happen? So now I want to find a point which sits in the shell, right? In the shell of this thing. But I want the ball, a ball of controlled radius outside of the shell. So this is kind of close in the original. Sorry, I should have said something like more this. Yeah, we go closer to the boundary, and then I want to find a ball which sort of doesn't overlap the boundaries here, but sits nicely, so of controlled radius, sits nicely in the original ball. So, and the point is, it is not guaranteed by the triangle inequality. So it just says that there are sort of sufficiently many points that are controlled, sitting in the controlled way in boundaries of balls. Okay, so let me state now the real theorem. So I will give you an example of the situation here. This is maybe a little bit harder to understand, it's a little bit formal, this definition, but I will give you an example which goes beyond somehow Hadamard manifolds, and the real theorem is the following. The theorem let gamma be a finitely generated group with non-elementary action on a hyperbolic space X. Assume that the boundary of Gromov boundary of X, so there's no assumption on X, has finite Assouad dimension, or say it's doubling. Since I didn't talk about Assouad dimension, is doubling and 4. Then there exists a P bigger than 1 and an Lp space V such that the reduced cohomology of gamma with coefficient in V is non-trivial. So fullness, let me give you an example. So fullness is hard to control. Even for Hadamard manifolds, I actually don't know how to prove fullness, although the theorem applies to a group acting on Hadamard manifolds in a non-elementary way. But here's this point. So the fullness is a bit formal. You can replace. So fullness is not invariant under Lipschitz map or by Lipschitz map. You can replace fullness. So it's a physis that dx is by Lipschitz to a full metric space. Yep. Oh, yeah, so that was, I screwed it up. So this was, of course, NY. Thank you. I screwed it up. Yeah, this thing is, you want this? Let me see. So it is a, thank you. So it is a bit, this fullness condition is a bit formal. Yeah, I know you don't need this. Sorry, this is correct. So so the point here is, so let me make the point here. It's correct. So the fullness definition is a bit difficult to understand. So what it means, so why do I want, what is the role of the y? I want to have a point which has distance r, fixed distance r to the original point. That is guaranteed by the y. So like, I mean, there could be point, there could be radii where there's nothing. Yeah, so that's a point. And I want to, so the whole thing is to capture that I have enough points. I need enough points. So I give you an example in a moment of a space which is full and some which is not full. And they're both Cantor sets. So you can have Cantor sets, but the point is really, I mean, you need to guarantee that you have enough points. And so the real theorem is, as I said before, so that you have this action here. If you have an action on this hyperbolic metric space, hyperbolic Gromov hyperbolic space, no assumption, not properness or anything, then you can construct representations with non-trivial first cohomology. And so let me tell you how this definition comes from. But before, let me give you an example of, or examples of spaces which have this fullness property. So a tree, say start a tree, say a tree of fixed valency. So every vertex has the same valency, say k bigger or equal than 3 has a full boundary. And then what does not have a full boundary is a tree which has a following property. So you start off with with maybe something that is branching like this. Then you go a long way along one of these legs here before you find another point which is branching. So there's a long segment where there's no branch point. So maybe the tree is a simplicial tree, but you have a segment where there's no branch point. You go quite a bit further out. Then you may have branching in one direction, but again further out, and there's absolutely nothing. Meaning, so you go further out, you go very, very long distance, maybe 2 to the power something like the original distance, and then you may have another branch point. And then you keep on going. So really the branching is extremely sparse. And if you construct such a situation here correctly, then you will see that the boundary is not full. It does not have this fullness property. But if you have a uniform, I mean, a tree with fixed valency, then you get the fullness. So it doesn't mean that so fullness doesn't imply that the space is connected, for example, or pathwise connected. So what is the idea of the argument? So I have a few more times to say something about what is the idea of the argument is. So the idea of the argument is you start with the homogeneous, or this alpha homogeneous measure. Mu on the boundary of this space. You get it for free. So there's a small caveat, or I should point out to you that so you start off with a measure which has, you start off, with a metric space which has this doubling property. It doesn't mean that this measure space admits such a measure. You need the space to be complete in the metric sense. But Bonk and Schramm showed that the boundary of a Gromov hyperbolic space is always complete. So you do get your measure. So you start off with a complete doubling space. Again, no assumption here. You get this alpha homogeneous measure. And then you want to say, okay, somehow the group now acts on the boundary in a nice way, in a non-trivial way. But I want the measure to be alphas regular and invariant under the group, or the measure class invariant under the group. Of course, this does not fit reality. So you have to do something. And now what you do is you use finite generation of the group to average the distance on dx and the measure. So what does it mean you average? So you write down a point, what's called a Poincare series. You write down the following thing. So e to the power minus, say now you take any Cayley graph here. You start with a generating set. This defines your Cayley graph, so a distance on the group itself, which has nothing to do with the distance on the space on which the group acts, but you just write down the following thing, e to the power minus as the distance between, say, gamma and the identity here. So you sum over all gamma. So this is going to be finite for S sufficiently large. So you get this convergent series, and what you just do is you take this series and you average your distance function. So meaning you sum up now the distance function as an average with respect to where the coefficients are in the series. So the new distance function that you produce on your space will be of the following form. So it will be of the form sum e to the power minus. So this is now the distance in the group, gamma and gamma. And now you take the original distance. So this is the distance on the visual distance on X. And you take the pullback gamma star of the distance. So the group gamma acts on the boundary as a group of homeomorphism. And now you just average your original distance with, so yeah, over the group, but where the averaging, sorry, I forgot the S here. The averaging is in such that the series here converges with this distance here. This defines the distance. Then you do the same thing with your measures. So you do this thing here. E to the power minus S, d of gamma E, gamma star mu. So you, the group acts on the measure. So you start off with this homogeneous measure, and the group acts on it. And now you realize, so you realize that if dx is full, then gamma acts C-quarsely conformally. Here you have to prove something. On dx for some C. So now this means that you can control the action on the measure because you have enough. First of all, you know that balls are mapped nicely to balls, meaning that you have the dilatation and you can control the dilatation using the mass of balls that are in the image of given balls. So you know, you get an understanding of how this group acts on the measure. So now you average over the thing and you see now what you do, what this does for you is at the end of the day, you end up with a measure which is alpha is regular for some new distance. And the group acts measure class preserving. With a controlled by the Nicodim derivative. So here you have a beautiful space. So you get a measure class preserving action for construction of Lp-cohomology. This is not quite good enough, but then you do something which is sort of familiar for all of, in particular to Bruce, for all of you who have ever thought about negatively curved, closed negatively curved manifold. The space where you do get the representation is, now you take the boundary, cross the boundary minus the diagonal with, yeah, I mean, with a measure of the form nu cross nu. So the nu is your new guy, the average measure that you start off with, times the function, say the function here is in two variables, and f is such that, and you have to show that you can arrange this, but this is due to the fact that the group acts C-quarsely conformally. So f is such that the Nicodim derivative of gamma in gamma with respect to this nu cross nu times f is uniformly bounded pointwise. So it exists almost everywhere and it's uniformly bounded pointwise. Above and below by positive constant. So it contained in C minus 1 C for C bigger than 0. Above and below, of course, is very important. And once you have this, then you do get a representation. Of course, I mean, it's not isometric, but I mean, so we know how to deal with making out of this representation actually an isometric action on LP space. The LP space will essentially be this guy here. So meaning functions, LP integrable functions with respect to this measure. So then you show that there is a large enough P such that actually you do get the co-cycle using the Nicodim derivative and the information that you have. And this gives you the cohomology that you want. And so I have 1 more minute to say, okay, I mean, so to what groups does it apply? It applies to many known examples, but also there's things like the mapping class group of a closed surface. So that is one contender. And presumably many other groups, because again, now due to work of people working in geometric group theory, they have a lot of mechanism to construct actions, say on quasi-trees. For example, quasi-tree is a space which is quasi-symmetric to a tree. And so once you control that this thing has finite Assouad dimension, and maybe it has this fullness property, then you're good with finding non-trivial Lp-cohomology. Thank you very much for your attention.
Are there questions? Thank you, Ursula. Are there questions?
Is there any way to control P? I mean,
No.
give it, no.
No, I mean, so
Why?
For those people who work in metric analysis and know that in order to get this homogeneous measure, you have to snowflake what you started off with. And you don't know how much you have to snowflake, meaning you have to replace your original metric by a power. And this goes, the control on the P goes completely out of control. So the dimension of somehow this, the homogeneous dimension of the measure, that is someone that somehow that gives you the P. But in order to compute it, I mean, so there's this sort of this going back to the Euclidean space, and you have to snowflake to do this. And this is how the way you snowflake gets the loss of control. If you can control the snowflaking procedure, then you're good, then you get a control from the original, say, the original dimension of your space. But again, I mean, there's all this sort of thing that comes from this construction and metric analysis, which is really hard to say anything concrete about it.
And I had a second question related to the mapping class group. So you said it applies to a number of mapping class groups. Why doesn't it apply to all of them?
It does. It does.
It does. Oh, okay.
Yeah, yeah.
That's then I misunderstood.
So I mean, so the Bestwiener and Bomberg showed that the boundary of the curve graph has finite Assouad dimension. So it is doubling. And then you prove that it's full also.
Is there any connection to Bogdan Nika's work where he, for hyperbolic groups, built actions in LP spaces?
That is 100% motivated. I mean, it's motivated by, this work is motivated by Nika's work and or by the work of Bonk and Schramm.
Any more questions? Okay, let's thank Ursula again and let's go for coffee. Welcome back, everyone. So the next speaker is another grandchild of Bruce Kleiner. It's my pleasure to introduce Gioacchino Antonelli. He's going to talk about isoperimetry for non-smooth spaces with curvature lower bounds. Thanks, Gioacchino.
Okay, thank you very much, Enrico, for the presentation. I have to say that I'm also a son of Enrico. That's why I'm a grandson of Bruce. And it's really an honor to be here to speak at this conference, which is amazing, so full of very nice talks. And it's my third week in Pisa. I used to live here 9 years ago. No, 9 years ago, from last year. I live in New York, but it's very nice to be back here and to speak about one of my favorite projects I've been working on the last 2-3 years, I would say, with a lot of co-authors. I'm not gonna tell all the names, but you can find them here. And yes, some of them also gave me some nice pictures to for this talk. Okay, so I'm going to speak about isoperimetry for non-smooth spaces with curvature lower bounds. And in doing that, I think I will also touch one of, or a couple of early works of Bruce for more than 30 years ago. So just to say that his production was really very like broad. Okay, so let me introduce the main protagonist of this talk is the isoperimetric profile. I'll be stick to the smooth Riemannian manifold case, okay, in this talk with a fixed volume measure and a perimeter measure. What is the isoperimetric profile? It's a function that associates to every volume, okay, the infimum of the perimeters of all the sets with volume V. In case you have a minimum of this problem, this minimum is called an isoperimetric set, okay? So this problem of finding minima of this problem is very old. It dates back to Queen Dido, as the legend usually acknowledges. Something new can be said on smooth Riemannian manifolds with the non-smooth technique, as I will show. So first remark, balls are isoperimetric sets in Rn. There are a lot of proofs of this fact. So you can compute explicitly the isoperimetric profile of Rn, which is some power of the volume times a constant that you can explicitly compute. Okay, so it's here. And okay, I'll be stick to Riemannian manifolds, but the definition of perimeter and isoperimetric profile makes sense in arbitrary metric measure spaces after the theory developed by the seminal works of Ambrosio and Miranda in the early 2000s, okay? Cool. So now let me give you an idea of why some lower bounds on the curvature should affect the isoperimetry of the space. And the point is that the Ricci curvature appears in the second variation of the area. Okay, so if you take a smooth set in a Riemannian manifold, and you take, I mean, you can give the second variation in a with more general variations, but I just decided to give it for enlargements. What is an enlargement? You take a set, and you just take the T tubular neighborhood inside or outside, okay? So this is ET, okay? If you compute the second derivative of the perimeter of the enlargements, you get the integral of the mean curvature square minus the second square minus Ricci. That's where the curvature of the ambient appears, Ricci along the normal, okay? To the set, and this led Gromov. I think that this is probably the first work in which you can see that there is a clear interplay between Ricci bounded below and the isoperimetry of the space. This is a preprint in the 80s, where Gromov showed the famous, celebrated Levy-Gromov isoperimetric inequality, leveraging on some ideas of Levy in the 50s. So he proved that if you have an n-dimensional complete Riemannian manifold with Ricci greater or equal than n-1, so it's compact, then you have this sharp lower bound on the isoperimetric profile, okay? So you have the renormalized isoperimetric profile is dominated below by the renormalized isoperimetric profile of the sphere, which is the model that has Ricci equal to n-1. Let me talk for a moment about the case in which the curvature is bounded above. And there is a celebrated conjecture that has resisted more than a century of attempts by many mathematicians. One of them solved it in the dimension 3, Kleiner, in 92. And but I'm never tried to really understand all the literature behind, so I'm just mentioning it because I think it's nice. So if you have an n-dimensional complete and simply connected Riemannian manifold with non-positive sectional curvature, it's conjectured that you have this sharp isoperimetric inequality. So the isoperimetric profile is bounded below by the 1 over n. This conjecture has been proved only in 3 cases, in the 26 in the case 2, in the 92 by Kleiner in the case 3, and in case 4 by Kroc in the 84, okay? So it seems to be a difficult problem. And okay, but now I will be back to non-negative Ricci. And I want to introduce the result that I'm gonna prove in this talk. I'm gonna prove the sharp concavity of the isoperimetric profile under non-negative Ricci curvature. This is the result. Very short. So if you have an n-dimensional complete Riemannian manifold with a non-negative Ricci curvature, then the correct power of the isoperimetric profile, the sharp that you can expect by seeing Rn, is concave, okay? This result has been first proved in the dimension 2 by Pansou and Bavard in the 86. And if you see, it's a remark in a paper where they compute the minimal volume of R2. And yes, this, so it's like, you can do this in the compact case in two-dimensional, and then it was generalized. It appeared in several works, notably by Morgan and Johnson and Ni Wang, and then before, Bale had proved it like in the general compact case with arbitrary Ricci lower bounds. The fact that, okay, the compact hypothesis is strongly used in all of these proofs because it leads to the existence of isoperimetric sets, okay? And I'm not giving the classical proof. You can try to do it if you want, or to see the references. But basically, you take the isoperimetric set, you use the second variation formula, and then you get the concavity. And those are the two main ingredients, okay? In the non-compact case, it was not known. We proved it with myself with Enrico Pasqualetto, Marco Pozzetta, and Daniele Semola. And the idea is that while proving this result in the non-compact smooth case, you really see the emergence of the non-smooth geometry at infinity. So you really have to deal with the stuff in the non-smooth setting. I'm giving this statement here for simplicity, but you can give it for arbitrary Ricci lower bounds, and even in your favorite non-smooth spaces, in RCD spaces, okay? Alexandrov spaces also. This is also in Alexandrov space with sectional lower bounds, okay? That's it. A quick overview, just to convince you why one should be interested in this cumbersome concavity, is because it leads to a number of consequences. I'm not going to comment on all of them. Notably, I want to, some of my favorites, like it leads to the connectedness of isoperimetric regions in Ricci non-negative, to uniform diameter bounds for isoperimetric sets. And you can use it, actually, you can use the technique that you use to prove this concavity to give a new proof of a sharp and rigid isoperimetric inequality on spaces with non-negative Ricci curvature, okay? Also, you can use it to give an alternative proof of Levy-Gromov isoperimetric inequality in the non-smooth setting. And which has been proved, let me so by Cavalletti and Mondino first in the non-smooth setting. Yes. So, okay. So we saw that the problem is the existence in the non-compact case. So as soon as we have existence, we can run the classical proof and we are done. So what about existence in the non-compact case? Maybe we are lucky and we do have isoperimetric sets in non-compact, non-negatively curved space, and that's not the case. Non-existence can happen in a rather strict sense as soon as the dimension is greater or equal than 3. This is a result that I got with Federico Glaudo last week, and okay, it's just we already obtained it. We posted on Archive last week. We constructed a complete non-compact Riemannian manifold with positive sectional curvature that has this very strange behavior. It has isoperimetric sets for volume greater than 1, and it doesn't for volume less than 1. So really, this is something that tells us that all the machinery that we developed 1 year ago is really necessary in a case of non-negative curvature, because non-existence can happen, and so you have to deal with it, okay? And the hypothesis is sharp because Manuel Ritoré proved that for surfaces, the same result is true. So you do have existence for all volumes, okay? Now let me show you this rainbow surface. And so what is the idea? I'm not going to comment widely on that, but the idea of the construction is this. You take an open convex cone in the upper half space, let's say in R2, and you multiply by R, okay? So you want to construct the manifold in such a way that your isoperimetric sets want to escape there. So, but first, let's construct an example for which existence fail for the relative isoperimetric problem. And the example is a cone now, okay? So now I'm thinking about the space that is above this surface. So this is what you do. You take sigma times R and you cut it, and you have to cut it very carefully. It's not that every cut works. And then you produce a surface that is the boundary of a convex set that doesn't have a isoperimetric set for volume less than 1, if you are able to cut it in a nice way, in such a way that your isoperimetric set really wants to go at infinity in this direction. So how do you construct the surface? You go one dimension above, you construct your convex body, you hope that you can do things in such a way that also if you take the Alexandrov surfaces, that is the boundary of this cone, doesn't have isoperimetric set for volume 1, and then you approximate with smooth Riemannian manifold. This is how we construct this example. It's important to know the concavity of the profile, also to construct this example. And yeah, so this is what I wanted to tell you. But now, okay, we might have non-existence, so we have to learn how to survive without existence. And this is an idea that I call like asymptotic mass decomposition. So basically, if you don't have isoperimetric sets, they want to escape at infinity. This is the idea. So we have to learn how to control the geometry at infinity of the manifold. And this is what we do with the notion that is nowadays very well used. It's the point, the Gromov-Hausdorff convergence. Historical note, correct me if I'm wrong. Gromov introduced this notion in his paper in which he proved that finitely generated groups with polynomial volume growth are virtually nilpotent, which is also something that is related to Bruce's works. Okay, and you have these. Okay, what does it mean that pointed metric spaces converge to a limit? It means that you can embed all of them in a big metric space in which you can detect this convergence as the Hausdorff convergence of closed balls around points. I'm not going to give you formal definitions. This is the idea. There are several definitions. All of them are equivalent in our setting. Okay. And yeah, you have to think this. You have this big space in which things are really converging in the Hausdorff sense. Now that we have this convergence, I have to give you a compactness theorem. This is what Gromov did in 81, and he gave this slightly more general version of this compactness theorem. He proved that something that, as a corollary, is that a pointed and dimensional Riemannian manifolds with Ricci lower bounds, this might be also negative lower bounds, is compact in the pointed Gromov-Hausdorff topology. So this is the notion that we are using. So to detect the geometry at infinity of our space, we are taking a sequence of points that are converging in some Ricci limit space at infinity where our isoperimetric set is going to live. Any such limit is called a Ricci limit space. And if you have a uniform bound from below on the volume of unit balls, it's usually called the non-collapsed Ricci limit space. And let me say that the structure properties of those limits were started to be studied by a series of beautiful works, 4 works by Cheeger and Kolding in the late 90s, exploiting also previous works. And there are some recently found results on the structure of these spaces that I think Jeff Cheeger is gonna tell you something about that tomorrow. Okay, I'm not gonna say anything about that. And also, let me say that the study of the geometric properties of these spaces gave the impulse to study geometric properties, geometric aspects of the theory of CD and RCD spaces that I'm not going to introduce now because Sergio introduced it yesterday, and also the focus of this talk is, I think, on how you get this in the limit and not starting from the very base space. Okay, so you have, I mean, those are the basic references, I mean, where everything probably started. But there are also some precursors, but I'm not going to mention any of that, okay? And let me say again that all these results that I'm presenting, all in the RCD space, okay? Cool. So what happens when the set want to escape at infinity? Basically, you have concentration compactness. So first observation, something that I'm tacitly using, is that under non-negative Ricci, the isoperimetric profile is non-zero if and only if you have a uniform lower bound on the volume of unit balls. This is an exercise that can be done with Bishop-Gromov. So if you have a sequence of balls that escapes at infinity and that loses all the volume, then the isoperimetric profile is constantly equal to 0. So this is an assumption that I will always take, I mean, the inf of the volume greater than 0, because doesn't trivialize the problem. So it's safe to assume that. If you don't have that, then the isoperimetric profile is 0, the power is 0, and it's okay. So what happens when we have a complete n-dimensional non-compact Riemannian manifold with non-negative Ricci, and we do have this uniform lower bound? This is what happens. Either you have an isoperimetric set on your manifold, or you get it in a limited infinity, okay? So if I stated it this way, if there is no isoperimetric set of volume V in our manifold, then you get a limited infinity, so you get a diverging sequence of points and a pointed Gromov-Hausdorff limit such that you do have an isoperimetric set there of volume V, and the isoperimetric profile of two spaces coincide in V, okay? So now we have a space where we have an isoperimetric set, okay? So if we have it on our manifold, we do the second variation, we are happy. Now we have it on a limit, and a limit might be non-smooth. In our examples, they are cones. You can have cones, okay? So let me show you a picture. It's like, you have this non-negative Ricci curve manifold, and what happens if you don't have isoperimetric sets is that you find a limit at infinity, which might be non-smooth, and an isoperimetric set, which might be non-smooth as well, that has volume V, and you have that the two isoperimetric profile coincides at volume V. So let me mention that, okay, analogous results or general settings, but this result has also an history. I think that the first two, no, okay. The first to notice that you have this loss of mass at infinity where Ritter and Rosales. Then there are ideas of Nardulli that prove the version of this result when you have a strong control on the geometry at infinity of the manifold, and then we refined all of these ideas using the Gromov-Hausdorff convergence, and it's proved by concentration compactness. Okay, now we have an isoperimetric set in a non-smooth space, and now we have to do the difficult step. Okay, the difficult step is survive without second variation, because it doesn't. I mean, you lose all the smoothness. You might lose all the smoothness. Okay, and this is probably the main technical part of our work, and this is something that I did together with Enrico Pasqualetto, Marco Pozzetto, and Daniele Semola. We encode the information of having mean curvature H with Laplacian bounds on the distance function from the isoperimetric set. So I said, okay, what is NCR-LS? It's like it's a non-collapsed Ricci limit space, because now we ended up in a non-collapsed Ricci limit space with a non-negative Ricci curvature. In a sense, it's the limit of space with non-negative Ricci curvature. Then we can prove that for some H that you have to think as substitute of the mean curvature, the Laplacian of the distance from E is greater or equal than this quantity. This quantity is what you get in Rn. If you take a ball and you compute this quantity, this is the mean curvature of the enlargement of the ball. So this is sharp, okay? So this is how you encode. I mean, this is equivalent to say that the mean curvature is equal to H on the boundary when you have non-negative Ricci curvature in the non-smooth setting. So this is really a substitute, a non-smooth substitute of this information. And you have this in a distributional sense. What does it mean? The integral of the phi against the Laplacian is minus the integral of the gradient. You have a notion of how to multiply gradients. So this is, okay. So you have these bounds that are sharp on the Laplacian on the distance function. And let me say some history about that. So probably, okay, the idea of encoding bounds on the curvature with inequalities on the Laplacian of function is probably old. It dates back probably to the 50s to Eugenio Calabi. It has been used several times in the literature in the proof of splitting theorem by Cheeger and Gromov, in this work by Hu in 79. It has been used by Caffarelli and Cordoba in 93. Also, the idea of encoding mean curvature with the equalities on the Laplacian of the distance function was kind of divined by Petrunin in this research announcement, this very short research announcement, in which he suggests how to prove, and he proves actually, the Levi-Gromov isoperimetric inequality on Alexandrov surfaces, on Alexandrov spaces. And let me also mention that I say, okay, I said, let me go and check the early works of Kleiner, and I realized that you use this technique in this paper, the 92. Correct me if I'm wrong, but where you prove like a compact version of the Cheeger-Gromol splitting theorem. This is like he used the Laplacian, these Laplacian bounds. Okay, and yes, now I will not say anything on how to prove this because it will probably take a lot of time. Let me give this consequence, and so this, and where else I tried to look in the literature if there is a place where it is explicitly stated this proposition, but I didn't find it. So if you are able, if you know something, yeah, please tell me. But this is something that we explicitly written in this recent work with Glaudo. The fact is that as a consequence of that Laplacian lower bounds and upper bounds on the sets, you can integrate this using a Gauss-Green formula and using some ODE argument to show that this quantity as a maximum at t equals 0. What is this quantity? You see, we are producing, so we want to prove that the isoperimetric profile is concave. This is giving us a line that is touching above our isoperimetric profile, and thus is going to be concave because of this property. I think this is a nice way to think about the concavity property, and this really comes from the Gauss-Green formula and some of the analysis in the previous slide. This quantity is even monotone for t greater than 0. Okay, so this is like this is the derivative of the profile to the n divided by n minus 1 at the point, kind of the derivative if it's everything, as if everything is integrable. And let me say that we have this property in non-collapse regime space, we have it in RCD spaces, and this is really exploiting all the machinery in the non-smooth setting that has been developed. As of today, we have a very well robust theory of codimension 1 surfaces in RCD spaces by these works by Ambrosio, Bru, and Semola, and Bru, and Pasqualetto, and Semola. Let me conclude how to prove this concavity. So let's fix a volume. Let's do the most difficult case, which is the case in which you don't have an isoperimetric set. You have it in a possible non-smooth limit at infinity. So you do get a limit at infinity of M where IM and IX are touching at V, and you have an isoperimetric set of volume V in X, okay? Now you take H to be a mean curvature, as we defined by using the Laplacian distance function, and you have this picture. You have the isoperimetric profile raised to the power n divided by n minus 1 in M. So this isoperimetric profile is always bounded above by the 1 of X by simple approximation. So it's always bounded above by the perimeter of these enlargements. So you have this red function that is above this black function, okay? And what is the property that I was telling you before saying to us? It's saying that this function is bounded above by a line that has this slope. If you put on the x-axis the volume of the enlargement. So we explicitly produce a function that is squeezed between the isoperimetric profile and the line. The isoperimetric profile is continuous. Then you use the viscosity theory to say that it's concave in the classical sense. And this works also in the compact case, because you do have an isoperimetric set, you have the same picture. Okay, so this is a unifying proof for all the two cases. I'm almost done. I want to mention a question I still don't know the answer. About the existence. So we produce this example of existence, but the question of if you have isoperimetric sets, at least for large volumes, remain in general for Riemannian manifolds with non-negative sectional curvature. We know that it's true for manifolds that have an asymptotic cone that is one-dimensional. We know that it's true for manifolds that have an asymptotic cone that doesn't lose dimension. We don't know anything in between. And we do know that we can't expect the existence for small volumes by the counterexample that I showed you. And this is all that I want to say. Thank you for the attention.
Thank you very much, Gioacchino. Are there questions?
Yeah, I have a question. In the RCD setting, how will you translate the non-triviality condition of having a lower bound on the volumes of balls of radius 1?
Okay, you say, actually, we proved that, we proved this in the setting of non-collapsed RCD spaces. So when the reference measure is Hn, so you simply ask that the infimum of Hn of the volume is strictly greater than 0, and everything works. I think there is already enough technique to do that with arbitrary measures anyway.
Okay, thanks.
Other questions?
Thanks for the very nice talk. This is a kind of a technical, hopefully easy question. So when you the picture you showed in the last slide, t was both above and below 0. So is ET for negative t the enlargement towards inside, and then for positive t it's towards the outside? Okay, all right. Well,
The ET is the enlargement inside. It's the set. So for t negative is the set of points that are at distance at most negative t from the complement.
Okay, all right. Thanks.
Gioacchino, in the question that you asked at the end, if we should expect existence for large volume, this lower bound on the volume, on what do you expect to be depending on? Because there is no volume, there is no
the low. So you mean the first volume for which you do get existence? I expect it to depend on the geometry at infinity of the manifold, because in our counterexample you have spaces at infinity. Those are really causing the lack of existence. You have spaces at infinity that have a density in some point that are strictly less than everything that is on the manifold. So it's really convenient to go there. I don't know, but it should really depend on I think it really depends on the manifold you're looking at, probably just on this quantity. I don't know.
Yeah, but if this density might be 0 at some point.
No,
then...
it cannot be 0. Cannot be 0. No. Because you have a uniform lower bound on the volume of the unit poles, so you do get always a uniform lower bound on the unit poles at infinity too. But maybe I didn't understand.
Yeah, we can talk about it.
Yeah, we can talk about it.
Any more questions? Okay, let's thank Gioacchino again. Okay, let's resume. I remind you that tonight there will be the social dinner. If you think you are not coming anymore, please let us know so we can maybe give your seat to somebody else. If you instead think you are not registered, come and talk to me. Okay, let's start back with mathematics. So the next speaker is Nicola Cavallucci. He's going to talk about convergence and collapse of cut zero spaces and groups. Thanks, Nicola.
Thank you, Enrico, and to order the organizers for the invitation. So the plan is to show no proofs, but a couple of examples. And I start with a baby case, which is still not completely trivial, and it's the manifold case. Then I move to the main part of my work, which is the cut zero case, and I propose a compactification of cut zero actions. Of course, this has no meaning till now, but let's see the problem. So let's start with the manifold case. I fix a simply connected Riemannian and manifold with double bound sectional curvature, -1 from below and 0 from above. I have a sequence indexed by J. On each of these spaces, I have a group, discrete and co-compact. D0 co-compact simply means that the diameter of the quotient, which is an orbifold in general, is bounded if the group is torsion-free is a manifold. And you can see, in that case, you can see the group as a fundamental group of the manifold. So we are dealing with the universal covers of compact manifolds with that bound on the curvature. And we consider equivariant Poynter-Gromov-Hausdorff convergence of these universal covers. Now, Poynter-Gromov-Hausdorff convergence was more or less defined by Gioacchino before, and I'm not going to define it. Equivariant is the same, but you take into account also the group actions, and you have this notion. In this setting, so when you have a double bound curvature, this convergence is equivalent to the Gromov-Hausdorff convergence of the quotient. So if you want to think about that, it's okay. And what we want to do is to say something or everything about the limit space, the limit quotient, and the limit group. Now, the difficult part here is that I'm not assuming anything on the injectivity radius, so anything, just the bound the curvature, and in general, the limit group is not discrete, and so the limit space is not the universal cover of this space. There is not a natural relation between these two. So we have to say something, okay? Now, this is a theorem, but we can take it as an assumption. There are just two cases we have to take into account, and they are the non-collapse and the collapse cases. They differ from the behavior of the injectivity radius of the quotient. So either it goes to 0 or not, okay? In the non-collapsed case, everything is easier, because in that case, the limit group is discrete, is actually discrete, and isomorphic as an abstract group to gamma j for j big enough. And we have also that the X infinity is a C1 manifold, even better. And so the quotient is a C1 orbifold, and we have diffeomorphic stability. So in that case, we can say everything, okay? Now, what is the prototypical example we should have in mind of a collapsed case? I took the hyperbolic space, Hn times R, but you can take everything you want. Just for simplicity, we take the hyperbolic space. And as a group, we take a fixed fundamental group of an hyperbolic manifold times a group of translations acting by the translation of length 1 over j on the R factor, okay? The quotient is a fixed hyperbolic manifold times a small circle. And of course, here we are collapsing because the circle factor is making the injectivity radius going to 0. Okay. Okay, this seems really easy as an example, but actually this is the only example. It exists, and this is a theorem, which more or less was done by Bujalo. We just refined it with Sambusetti, and it says the following. There exists a parameter, iota 0, which plays the role of a lower bound injectivity radius. The upper bound injectivity radius, sorry, depends only on the dimension and the diameter, such that in our situation, if the injectivity radius is sufficiently small, smaller than iota 0, then let's focus on this. We have a splitting of a non-trivial Euclidean factor, so exactly as above. And moreover, we can find an abelian, free abelian group, which is normal. This is the important fact, normal in gamma of positive rank. And maybe it's not exactly a product like that, but a finite index with bounded index, that is the bounding on the index of gamma, splits as a discrete group on the Y factor and a lattice on the Euclidean factor. Okay, so up to finite index, uniform finite index, that is the only example you can have. Okay, now, couple of comments. The main difficult part here is to prove 1. Once you have this, 2 is for free, and also 3 is known, but without a uniform bound on the index. And I can bound uniformly the index just because I can prove that the class of isomorphism of these groups are finite. So you know that each of them splits, and so there is a uniform bound on the index of this subgroup. But I don't know a proof which does not use this. I don't know if you can help me. Okay. Now, why compactness, uniform compactness, is needed? Because we have this example. This is the prototypical example of a graph manifold. You take an hyperbolic manifold with boundaries of length epsilon, and you take the product with a small circle, another copy of it, and you glue the torus boundary by changing the order of the circles. what you get is one of our manifolds, but also here we have it's fibered by circles, okay, by flat circles, but the fiber is not a product. Okay, so it's not, it doesn't fall in the conclusion of the previous theorem. And the problem here is that there is this hyperbolic part, and when you want epsilon going to 0, the diameter of this part has to go to infinity because of the hyperbolic geometry. And so if you have a bounded diameter, this cannot happen, and it never happens. Okay, questions on this part? Good. And now, with the theorem, we can describe what is the limit of a sequence of collapsed manifolds under our assumption. And first of all, the limit space splits non-trivial Euclidean factor. Well, because every space splits a non-trivial Euclidean factor, the splitting goes to the limit. Of course, the limit group is not discrete. Why? Of course, because you can imagine that the injective radius goes to 0 if you have smaller translations as before. And the smaller translations in the limit should create a continuous parameter of translations. And this is against the discreteness. But still, we can control what is the connected component of the identity. So what are these continuous part? It's one parameter groups in the limit. It is exactly the group of isometries that acts as the identity on this factor and every translation on this part. So our space, M infinity, which is the quotient of the limit space by the limit group, can be obtained by first quotienting by this normal subgroup. So we are erasing the Euclidean part, and then we quotient the remaining space, which is this one, by this group. And in this case, this group, which is a priori is only totally disconnected by definition, is discrete. Okay. And because of the bound on the index, we have this situation. Maybe it's more geometric in the quotient. So we have our sequence of manifolds that are converging to the limit space, and there is a finite cover, bounded degree, which splits metrically as something times a flat torus. And these manifolds converge to an infinity times a point in the following sense. This part converges to this part without collapsing, so as in the previous theorem, and these fibers collapse to points. So and then there is another cover there. So up to finite cover, the only thing that can happen here is that there are some flat tori that are going to 0, that are disappearing. Okay. And this more or less solves the question for the manifold case. Now, what can we say in the K0 setting? I start with a proper geodesically complete K0 space. So I'm not recalling what is a K0 space, but it's a replacement of an upper bound by 0 of the curvature. Geodesically complete means that every geodesic segment can be extended to a geodesic line. So it's natural for manifolds and for complete manifolds, this. And the packing condition, we saw it in many talks this week, but simply means the following. For any point, you take the ball of radius 3 R0 around the point, and you count how many disjoint balls of radius R0 you can put inside, and you want that this cardinality, the cardinality of these small balls, is uniformly bounded independently of the point. Okay, it's a very weak replacement of a lower bound the curvature, and now we have as before a discrete and co-compact group of isometries, and we are in the same situation as before. I would just want to say that if your sequence is packed, you in that meaning you always have a subsequence that converts to something, and if your sequence is converted to something, then there is a uniform packing. So it's just the minimal assumption you can ask, that packing condition. Okay, and the question is the same as above. Can we say something about this space? Can we say something about the limit group? Okay, same setting, more general. So we replace the upper bound by the K0 condition, the lower bound by -1 by the packing condition, and the smoothness by this setting. Okay. Now, there are differences, but still we can control what happens. In the non-collapsed case, as before, the injectivity radius of the quotient is not going to 0. In that case, the limit group, gamma infinity, is no more discrete. Before it was discrete in the manifold case, now it's just totally disconnected. And so we can say that the quotient is actually the quotient of the K0 space with all nice properties I said before, by this totally disconnected group. And maybe it's easy. I don't know. You can imagine that if there are no isometries that are moving every point by a small amount, the limit group is totally disconnected, cannot have connected component, but it's not completely trivial. And it's optimal because there are examples like this one. So regular trees, in particular K0 spaces, geometrically complete, where you can find pairwise non-isomorphic lattices, one inside the other. So they have all uniform co-diameter because they are inside the first one. And in this case, the limit group is really non-discrete. So they are very different groups. And this is just a thing that cannot happen in the manifold case, but here we have. Okay. Now, what happens for the collapsed case? There are differences also in this case. The theorem is really similar to the manifold case, but what are the differences? Okay, if the injectivity radius is small enough of the quotient, then we can find the free abelian group, subgroup of gamma of positive rank, which is just commensurated, okay, not normal now. Commensurated means this thing that for every element of the group, the index of A intersection GAG minus 1 is finite in both these groups. If the index is 1 is the normal condition, but this is more general, okay? Nevertheless, the space splits a Euclidean factor as before, and it is no more true that gamma split or virtually split, a subgroup of gamma splits as an action on Y and a lattice on the Euclidean factor. This is the case if the full isometry group of the K0 space is a Lie group. When does it happen? For instance, when X is a homology manifold. But when X is a 3, this is not the case. Okay. And now, yes, the proof is completely different from Bouguereau's proof in the manifold case. In that case, you have to find a normal subgroup. A normal subgroup is much easier to find because essentially you can say, okay, those are the generators, check that they are normal. Here you have to find this commensurated subgroup, and there is no natural candidate. Okay. Now, okay, this is the second example I want to show. Don't worry about this group, it's just a presentation of this group, but let's focus on the action of the space. So the group is generated by 3 elements, A, B, and T. A and B commute, and there are other relations. Now we take R2 on one side, and the regular 3 on the other side. I drew it valency 3, but I think it's 10, the real example, just to understand what happens. We make A acts as translation of length 1 on the Euclidean part, and as an isometry that fixes one vertex of the 3, but it has infinite order. This can be done by swapping edges continuously up to the infinity. Okay. B does the same. It moves by 1. It's a translation by 1 in the orthogonal direction, and do something similar here by making them commute in any case. And T now is an hyperbolic isometry on the 3, and here is a rotation which sends some sublattice of the group generated by AB in another one. And because of that condition, you can show that T has dense orbits. Okay, it is not a rotation by a rational angle of pi. So this is what it means, that gamma, the action of gamma on this product is made like that. On this part, the action is not discrete because of the presence of T. On this part, the action is not discrete because of the presence of A and B, but in the product, it is discrete. Okay, and even torsion free. Now, it's possible to prove that this group does not have normal subgroups and does not virtually split as Euclid Z2 times something else. But you can do the same construction by taking these translations of length smaller and smaller. And so you get something with injectivity radius going to 0. Okay, so this shows that here you cannot get normal, and here you cannot get the splitting. However, more or less, this theorem says that this one is the only example, the only new example that exists. And indeed, we can describe also in this case what happens. In the collapsed case, the limit space splits because every space splits. Here it's more difficult maybe to describe what is the connected component of the identity, but it's the same as before. Okay, so you have this nice description. And so as before, we can write the quotient space as the quotient of x infinity by gamma infinity. First of all, we quotient by this normal subgroup. We erase the Euclidean factor, and then we remain with that. A cat-0 space with all the nice properties we had before, quotient by this totally disconnected group, and this must be totally disconnected. In this example, you are erasing this part, and you are taking this totally disconnected group, more or less. Okay, so must be totally disconnected. And if you want to refine the description in the manifold case, we have to assume first that the geometry group is Lie, and then that the groups are non-singular. Non-singular simply means that there exists at least one point with trivial stabilizer. In general, it's not the case. I don't know spaces where cat-0 spaces where the geometry group is Lie and a lattice has not this property, is singular, but maybe they exist, I don't know. And so you have a description of all these quotients. For me, is sufficient. And what we did, now we pass to the compactification. What we did, we studied the class of quotients of proper geodetically complete packed cat-0 spaces by discrete and zero co-compact groups, right? We discover, I think, that if we define this class, the class of totally disconnected, and here I had an assumption, unimodular group acting on the same spaces, then if you have a converging sequences of these elements in C disk, discrete, okay, two element space, then the limit space is the quotient by cat-0 space by totally disconnected group, and this is what I showed before. And moreover, you can say it is a unimodular. Unimodular means simply that the NER measure is the invariant. It seems just a useless addition to the theory, but actually, why you get unimodular here is important. And this is because of the following theorem, which is going to appear, that now, instead of starting from quotients of cat-0 spaces by discrete groups, we can start with quotients of cat-0 spaces by totally disconnected unimodular groups that appear naturally in this theorem. Now we have seen that. And you can redo all the same machinery, and in the end, you get that the limit space is still quotient of a cat-0 space by totally disconnected unimodular group. And for that theorem, unimodularity is important. Okay, so we have found what? A compact class which is closed on the Gromov-Hausdorff of convergence. So it's closed, and it's the main fact that compact is easy. A compact class that in particular contains all the quotients by discrete groups. So it's a natural compactification of this class. Okay. And you have a lot of properties on this compact class. Now I'm going to stop, but before, just 2 comments, very quick comments on the difficulties of this proof. First is technical fact that you have to control the unimodularity property under Fukaya convergence, equivariant Gromov-Hausdorff convergence, and a priori there is no reason why this property should pass to the limit, especially because in the collapsed case, you start from totally disconnected group or discrete group, and you get something which has a connected component of the identity. So the nature of the group is completely different in the limit. Okay, so you have to do something to show this. And the second fact is that now you work with totally disconnected groups, non-discrete in general, and every strategy that works in the discrete case starts, for instance, from the Margulis lemma that we have saw in Sergio's paper, Sergio's talk. And so this is a problem because you start at the beginning of the proof. So what I did, for instance, I proved a Margulis lemma, a generalization of Briard-Green-Tau Margulis lemma for totally disconnected groups acting on proper spaces. And after that, you on cat-zero spaces, you refine the theory, and you can more or less copy what you did in the discrete case, but you have to do some modifications. So I stop here.